Good morning.
Good morning. Hello, Keith.
How
How are you?
Good.
Good. I'm fine here also.
I'm good. Sorry, I'm a bit late.
That's no problem.
Good.
I think
Do we have members in? I see that we already have 37 participants here.
we have participants around how many today?
Oh, okay.
That's joining our forum already around 30, yeah, more and less.
Oh, okay, that's fine.
Some of my colleagues will follow, yeah. Some of them still have a lecture, yeah.
Oh, okay, that's fine. I think they will catch up with us.
Okay, yeah. Maybe to save the time, I will open the session first, yeah. Assalamualaikum warahmatullahi wabarakatuh, student. Today we have the second lecture from the Dr. Mehlana from Department of Chemical Technology, Faculty of Science and Technology, Midlands State University, Zimbabwe. I think I read some of the CV, some of the track record of Dr. Giff last week also. He was a lecturer at the Faculty of Science and Technology, Department of Chemical Technology at Midlands State University, and he received his PhD degree from University of Cape Town, South Africa, PhD in chemistry, and he also received some prestigious awards from the research grant from Swedish Research Council. Very nice. And in 2020, he became a FLAIR, or he received FLAIR Collaborative Research Grant from Royal Society. And in 2019, he was selected as future leader as Afghan independent researcher from FLAIR also, Green Royal Society. Yeah. And his research expertise is in from frameworks, from the synthesis and then characterization and some application in sensing and in carbon dioxide utilization. Yeah. In this occasion, he will speak about how to use MOF in the application of CO2 catalytic reaction for CO2 to become fine chemicals, maybe like that, or how to utilize the carbon dioxide using MOF material. Okay, I give you around 90 minutes here to present about your work about MOF and application in carbon dioxide utilization. Thank you. Now it's your time, Keith.
Thank you very much for the presentation. So I'll try to share my presentation now. Remember in the last presentation, I talked more about sensing, and I touched briefly on application of CO2 in carbon dioxide utilization. So today I'm going to continue on that, but of course, I will talk more about how we can use metal-organic frameworks to convert carbon dioxide to useful chemicals. Yeah, I think that will be my talk today. And of course, I'll also talk about the mechanisms involved in CO2 hydrogenation. So I'm from Midlands State University in Gweru, Zimbabwe, and my research focus on carbon dioxide capture and conversion into fine chemicals. So why carbon dioxide? I think we all know about climate change and global warming. These threaten our existence on this planet. Therefore, there is need to find new technologies that can be used to reduce the levels of carbon dioxide in the atmosphere. This can be done through various ways. But of course, if we want to achieve net zero emissions by 2050, as has been advocated by different countries, such as those in the European Union, I mean, we can look at wind power. We can use wind to generate energy. We can use electric cars. We can also use solar power to generate electricity. So it means most of these emissions that we are getting at the present moment that causes climate change or increase in temperatures are due to the primarily burning of fossil fuels for energy needs. This has been causing soaring temperatures and unfavorable weather conditions in some parts of the world. So if we want to achieve zero net emissions, we need to look at different strategies. One strategy cannot only work. So we need to look at how best can we utilize this carbon dioxide that is emitted into the atmosphere. For example, if you just look at there are countries like emerging economies, they use a lot of coal to produce energy. And that process generates a lot of carbon dioxide, which is emitted into the atmosphere. So how do we harness that carbon dioxide? That is the question. How can we harness the carbon dioxide? Can we use technologies to store the carbon dioxide underground? Can we use carbon dioxide as a source of fuels? So this is what we are looking at in my research project. And of course, there are various ways of utilizing carbon dioxide, but my talk today will be more centered on using carbon dioxide to produce formic acid or formate. So in general, the project, what we do is if we think of manufacturing industries, such as the cement factories, such as industries which generate power, they do produce carbon dioxide into the atmosphere. So what we can do is we can develop technologies in which you have your MOF embedded, and that MOF that is embedded will then capture the carbon dioxide. And of course, we can also get hydrogen from water splitting for hydrogenation purposes. So the reactions that takes place within this MOF will then result in value-added chemicals such as methanol, formic acid, etc. So this graphic was designed by Professor Lars Armstrong at Chalmers University in Sweden. All right. So my research, I have people that I work with, or my collaborators from different countries. You can see here we have Professor Susan Bourne from the University of Cape Town. She was my PhD supervisor. She has expertise in supramolecular chemistry and crystal engineering. We also have Professor Lars from Chalmers University of Technology in Sweden, who has vast experience in reticular chemistry, as well as MOF synthesis. Dr. Makubela of the University of Johannesburg is an organometallic chemist, and of course she has expertise in catalysis and green chemistry. And of course, I am the principal investigator. My role is for project conceptualization and design, and of course I do synthesis and characterization of MOFs and also supervision of students. So our goal is towards sustainable catalytic transformation of carbon dioxide to high value chemicals. So we have done quite a lot of work on this, and we myself and Dr. Makubela, we do supervise quite a number of students, both master's students as well as PhD students. All right. So in my previous talk, I highlighted the sources of carbon dioxide, and I've said that most of this carbon dioxide actually comes from the burning of fossil fuels. But of course, there are other industries such as the cement manufacture, natural gas system. All this also contribute towards the emissions of CO2 into the atmosphere. At the present moment, we are pumping about 40 gigatons of carbon dioxide into the atmosphere on a yearly basis. So that's a very huge number to think about. So we need to find technologies that we can use to capture and convert carbon dioxide to high value chemicals, which can be useful for our industry. For example, if you think of methanol, it's actually a clean fuel. it burns and it produces less emissions. We also have a format which can be used in the industry for various applications. So these fine chemicals are very, very important so that at least we don't just let the carbon dioxide into the atmosphere, but of course, we harness it by recycling it for other uses. So in this diagram here, you can see some products of carbon dioxide utilization. If we have the industry can emit carbon dioxide, the power generation, and other systems such as anaerobic digestion. So we can utilize this carbon dioxide through transformation or direct use. Direct use, this is when you can use your carbon dioxide as a solvent, food, etc. And then, of course, you can transform the carbon dioxide through chemical or biological means. So today's talk is going to be centered on chemical transformation. I also work on biological transformation, but today I'm not going to talk about biological transformation. But in biological transformation, just briefly, what we do is we look at natural systems which are able to convert carbon dioxide to methanol. And then we then design new materials, what we call meta-organic frameworks, which can house these biological materials, and then we apply them in the transformation of carbon dioxide to methanol. This work is currently ongoing at the present moment and is being carried out by my 2 PhD students. But of course, today I'm going to focus on chemical transformation. In chemical transformation, we focus on inserting catalytically active materials in our meta-organic frameworks. Remember, in my previous lecture, I said that meta-organic frameworks have large surface areas. They are porous. So this allows us to insert molecular complexes or catalysts that are highly active, such as your ruthenium catalysts, pinza complexes, etc. So the whole idea is to capture and convert carbon dioxide to fine chemicals, or bulk chemicals or fuels. And in our case, we look at fine chemicals such as formic acid. Formic acid can also be used as an energy storage for hydrogen. We can also convert the carbon dioxide to methanol or ethanol, depending on the reaction conditions. There are also other means of dealing with carbon dioxide emissions, that is storage. So you can actually store your carbon dioxide underground. That is geostorage, but of course there could be some issues with the leaking of this carbon dioxide from underground. So we need to look at various ways on how best we can utilize carbon dioxide. I still believe that utilizing carbon dioxide is more beneficial than storing it underground, because we cannot deal with a situation whereby we don't use carbon, because life is carbon-based, and of course we just need to find ways of reducing the emissions in the atmosphere, as well as recycling the waste carbon dioxide that is produced to the atmosphere. Now, so in this talk today, I'm going to talk about what we started to do. That was in 2016. We started with this PhD student, Nyasha Makube. She already graduated. So the idea was to design these imine complexes, and of course, then introduce catalytically active metals on this site, with the hope of then using those complexes to make meta-organic frameworks. So Nyasha managed to isolate a number of meta-organic a number of complexes. As you can see, these complexes have some carboxylic acid functionalities, which then allows them to be used as ligands in MOF synthesis. And then what he then did was to form these diimine complexes of ruthenium using one of the ligands. Of course, she tested all the ligands that I have shown you here, and then we produced these ruthenium, iridium, and rhodium complexes. As you can see here, again, our carboxylic acid functionalities are very much free, which then allows us to synthesize meta-organic framework containing catalytically active ruthenium, iridium, or rhodium complexes. But of course, before we proceeded to do that, we tested these complexes to see if they are active towards the hydrogenation of carbon dioxide to form it. What we realized that, is that in this table here, we have entry 1 up to 3. Under the same conditions, we realized that complex C1, which is shown here, is more active towards hydrogenation of carbon dioxide to form it, with a turnover number of 270. And the least active was C3 with a rhodium metal center with a turnover number of 86. So what we then rationalized was that because these are homogeneous systems, so we can heterogeneize this by making metal organic frameworks. Already we have these carboxylic acid groups which are present. So it means if we say we can take a metal salt or a metal cluster, and then under appropriate conditions, we can react that metal salt with the C1, we should be able to form a metal organic framework with the ruthenium catalyst inside the pores. And of course, we should then apply it in the hydrogenation of carbon dioxide to form it as a heterogeneous catalyst as opposed to being homogeneous. So in that case, we tried to do that using different combinations of metal and solvents to make the MOFs, but we were not successful in isolating the required MOF. So what could have been the problem? We tried the traditional methods that are used in synthesis of MOFs, and especially the most appropriate method is if you want to isolate your single crystals, is sulfothermal. And it was so very frustrating because we didn't isolate the MOFs. What was happening was that during that reaction that we expected to give MOFs, this complex here was undergoing hydrolysis. Remember, this is an imine, so it went under hydrolysis. So that was the challenge that we faced with these complexes. We were not successful in making metal organic frameworks using these ligands with catalytically active sites of ruthenium, iridium, and rhodium. So we then shifted our focus from the diimine complexes to amines complexes. As you can see here, this is one of my PhD students. This is Malaza Spelele. She's currently tying up her work. She then managed to synthesize this amine complex, and then, of course, under appropriate conditions, with a copper DMF for 30 days. You can see this reaction took very long because this was a solvent evaporation technique. And already in this complex or ligand, you can see that we have the NN functionality, which is here, or which can allow you to synthesize a pinza complex inside the MOF. Why pinza complexes? Because pinza complexes in literature, they've been shown to be highly active towards hydrogenation of carbon dioxide. For example, if you have your ruthenium or your palladium can be inserted there, and then of course you can carry out your catalysis. So after 30 days, Spelele managed to isolate the MOF, and of course we ran the single crystal diffractometer, and this is what we got. We realized that the MOF is made up of a copper paddle wheel secondary building unit. We have a coordinated DMF molecule, which is coordinated to the copper. And of course, the water, which is represented by this oxygen atom, is also coordinated. And of course, you can see some tiny pores, though here, but of course, are very tiny. But of course, this diagram, it includes the coordinated water and TMF molecule. But of course, those ones can be removed to provide the active sites, which can actually enhance adsorption of carbon dioxide and other gases. So in this case, we're successful in isolating the MOF using the pinza ligand. Then in a different approach, Spey introduced the palladium site onto the NN site, And as you can see, and then we then, of course, under the appropriate conditions in DMAC and DMA for 60 days. This is a very long reaction. So, and again, this was carried out at room temperature. We managed to isolate some blue crystals with palladium as an active metal that we would expect it to have our hydrogenation taking place. And then we managed to look at the single crystal structure of the pinza MOF with the palladium 2 sites. And again, we realized that it has a copper pedal wheel. And of course, the copper is coordinated to the carboxylate moiety of the ligands. And of course, you also have some water molecules which are coordinated. And like I said earlier on, that these water molecules can be removed to provide open metal sites, and that also enhances catalysis because that increases the amount of carbon dioxide that can be absorbed to into the MOF. And you can also see here our palladium center, which is coordinated to nitrogen sites, and of course a sulfate molecule, which is also coordinated there. But what was the challenge with these materials is that because they were made at room temperature, when we apply high temperature or when we want to try catalysis, they tend to dissolve, which is not very useful for heterogeneous catalysis, because during heterogeneous catalysis, you don't expect your metal organic frameworks to dissolve, but these ones, they dissolve primarily because if you see the reaction took for so long, that's about 30 to 60 days. And of course, it was done under room temperature. So our next strategy now is to use these ligands that we designed, and of course, try to apply solvothermal reactions to form new metal organic frameworks that we can then use for hydrogenation of CO2 to formic acid. Now, I will now move on to some new porous MOFs that we made in our laboratory. These new porous MOFs were made by P.Y. Chuma, who graduated last year. She was a PhD student. And as you can see on this diagram here, you have some spaces that are inside the pores that you want to exploit for carbon dioxide hydrogenation. The whole idea is to insert highly active complexes of ruthenium or palladium, and then we carry out catalysis under heterogeneous conditions. So one of the ligands that we chose was this compound. As you can see, it has some nitrogen functionalities. And then we took this ligand, and under appropriate conditions with the lanthanum chloride, and we managed to isolate a MOF. And as you can see here in the MOF, the conformation of the nitrogen sites changes. This means that if you want to carry out methylation, it will be very difficult to do methylation, as this ligand has already been locked in the MOF with this kind of conformation. But of course, you can carry out what we call a cyclomethylation, where you want to activate that bond, the CH bond, so that your ruthenium can coordinate to the carbon and coordinate to the nitrogen sites, as given here. And one would ask, why not that site also? This will then depend on the nature of, on the size of the pores that are present in your MOF. If there is enough space, it means you can also have your ruthenium complex on that side of your MOF. But of course, if you also want to do that, you can introduce mesoporosity in your MOF. There are several techniques of doing that. Once you introduce mesoporosity, it means your MOF is able to accommodate bulky molecular complexes. So let's look at the crystal structure of this metal organic framework, which was isolated. As you can see, it's made up of a secondary building unit, which was generated in situ. And of course, in the space group, PNA 21C. And you have, the most interesting thing here on this is that you have your DMF that are coordinated, and your lanthanum is an 8 coordinate geometry, which is very interesting because the moment you remove your DMF, like I said earlier on, you generate open metal sites, which are very important, especially in the catalysis and the carbon dioxide adsorption. And of course, this is the packing diagram of the MOF. Here, what we are showing are the surfaces of the channels that are found in this MOF that we call JMS1. This is just some naming that we give our MOFs. And of course, these channels are the ones that we are going to exploit for insertion of our molecular catalysts, and of course, for the purposes of carbon dioxide conversion to formates. So we carried out this reaction here, cyclomethylation, to introduce the active site, which is our ruthenium 2, which would then apply, which would then be used in conversion of your carbon dioxide to formate. But how do we then know that we managed to insert the ruthenium into the MOF? We carried out some XPS studies. So what you would expect, you would then, in your XPS, you would look at the binding energy of your nitrogen and that of carbon. There must be a decrease in the binding energy of these if we had successful coordination of the ruthenium complex to the MOF backbone. And as you can see here, in the pristine MOF, or as made MOF, we identified the CN, right? And it's located here at 285 electron volts. And upon coordination of the ruthenium to the nitrogen, you then realize that there is a decrease in the binding energy from 285 electron volts to 285.3 electron volts. And then we also, so this was for carbon, this was for carbon from 285.5 to 285.3. That's for carbon 1s. And then we also looked at for the nitrogen 1s. We also expected the binding energy to decrease upon coordination of the ruthenium to nitrogen. And as you can see here, we have 400.9 in the as made MOF. This is before functionalization. And upon insertion of the ruthenium complex, the binding energy shifted to 400.06 electron volts, which confirms successful grafting of the ruthenium p-cymene complex into our MOF. Now, we also looked at how the structure would then change after insertion of this bulky molecular complex inside our MOF. This is the PXRD studies that were done on the MOF. And as you can see, we have the calculated pattern, which was simulated from the single crystal X-ray data. And of course, we also have the as synthesized or the as made material, which matches, clearly matches with the calculated, which also confirms some phase purity of the synthesized material. Upon activation, still JMS1 A, which is the activated material, still have is retained some of the peaks that are present in your as synthesized material. But upon functionalization with the ruthenium p-cymene complex, so RU28JMS 1A, you can clearly see some appearance of some new peaks, which shows some structural transformation that took place. And then, of course, if you take your activated material and then you soak it in DMF for 24 hours just to check for reversibility, you can clearly see that there is total reversibility in that transformation. We then did some carbon dioxide adsorption studies. So A is the results for the as-made MOF before you insert your ruthenium complex, and B represents results for the ruthenium functionalized MOF. So this is after inserting the ruthenium complex into the MOF. As you can see, at 298 kelvins, the amount of CO2 that is adsorbed by both the pristine MOF and the functionalized MOF is comparable. But you can see that the ruthenium functionalized MOF takes slightly less in terms of the amount of carbon dioxide when you compare it to your pristine MOF. And of course, interestingly, at 195 kelvins, the amount of carbon dioxide in both cases is very much comparable. I've looked at literature. You would expect, in fact, you would expect to have the amount of carbon dioxide adsorbed by this ruthenium functionalized MOF to be less than that of the pristine MOF, because here already you have your ruthenium complex, which is occupying the pores. So that should kind of reduce the surface area in which you absorbing your carbon dioxide. But in this case, they are very much comparable. And in literature, there are also reports in which MOFs, after functionalizing them, they may have a higher amount of gas being absorbed onto their surfaces. We then applied our MOF in heterogeneous hydrogenation of carbon dioxide to form it. And in this table, it shows different entries and reaction conditions that were used in the hydrogenation of carbon dioxide to form it. For example, entry 1, 2, and 3, they show the effect of the solvent on the formation of the product format. For example, at 90 degrees and a pressure ratio of 1:3, that is carbon dioxide to hydrogen, and a catalyst load of 15.6 micromole. If you have a THF as a solvent, you don't get any product that is being formed. And again, we also looked at toluene. There is no product that is formed. And of course, the moment you have ethanol as a solvent during your catalysis, then this is when we start to form some product. You can see that here we have 2.07 millimoles of format being produced, which is corresponding to 41.4% of the product. And then we also looked at the effect of the base that is used. In hydrogenation reactions, we normally use bases. You can try to use organic bases or inorganic bases. And then in this case, entry 3, entry 4, 5, and 6, they evaluate the effect of the base on the formation of the products. And again, we used potassium hydroxide as our base. And as you can see, potassium hydroxide is the one that is giving a high yield of 41.4%, followed by sodium hydrogen carbonate, that of 35%. It is very interesting to note that the triethylamine, which is normally used in a hydrogenation reaction, gave a very, very low yield of approximately 5%. What could be the reason for this? We noted that maybe the triethylamine does not have access to the metal hydride, which is located inside the pores of the MOF, because it's kind of bulky. So it's limited from entering into those sites to abstract a proton. Okay. And then we also did some control experiments in the absence of a catalyst, that is entry number 7. We also realized that no product is formed, which actually justify the need of a catalyst in this reaction. We also looked at the importance of the base in this reaction. In the absence of the base, again, that is entry number 8, there is no product that is formed. As you can see, the yield is 0%. Right? And then in the absence, that is end number 9, in the absence of carbon dioxide, so no product is also observed. So this actually confirms that the source of carbon from the format that we are forming is actually carbon dioxide, because in end number 9, you can clearly see that there is no carbon dioxide that was used. We only used the hydrogen, and of course, no product was also observed. And of course, the same also applies if you don't have hydrogen, you also don't get your product. And then entry number 11 and number 12 looks at the effect of the catalyst load. As you increase the catalyst load, as you can see here, as you increase the catalyst load, the yield of the format that is also formed increases, which confirms that this reaction is first order. We also checked the activity of the activated MOF. This is the one which does not contain your ruthenium complex inside the MOF. Interestingly, under optimized conditions, we realized that the lanthanum MOF is active towards hydrogenation of carbon dioxide to format. We also looked into literature to find out if there are any reports in which lanthanum has been used for hydrogenation of carbon dioxide to format. And interestingly, there are no such reports in literature. But of course, we are very much aware of other results on catalysis that the lanthanide metal ion has been used. So we thought this could be an error, and we did quite a number of experiments just to confirm that what we were obtaining was actually due to the lanthanum catalyzing the hydrogenation of CO2 to format. And we really confirmed that. We also looked at the effect of the ruthenium p-amine complex, and we realized that the ruthenium p-amine complex is also able to catalyze the hydrogenation of format, so the hydrogenation of carbon dioxide to format, and they, of course, with a very low yield of 24%, because this is a dimer. You know, with the dimers, they're not very active towards hydrogenation of CO2 to format. So these are the results that we obtained. And of course, during catalysis, we have evaluated different parameters for hydrogenation of carbon dioxide to format. We looked at the effect of pressure. As we increased the pressure, we realized that the yield of format that is produced also increases. And of course, an increase in temperature also results in an increase in the yield that is formed. So here we have the ruthenium functionalized MOF, which is being compared to GMS1, which is the pristine MOF. And as you can see here, at about 110 degrees, that's the optimum temperature for the ruthenium functionalized MOF. Beyond 110 degrees, you can see a drastic increase in the yield of format that is produced. This can be attributed to the decomposition of format at high temperature. Remember, this is an exothermic reaction that is taking place. Formation of formic acid is an exothermic reaction. So as you increase temperature, you should expect the format to decompose to give the initial reactant. So at 120, you can see that a drastic increase. But of course, with the pristine MOF, we saw a gradual increase in the amount of format that was being produced. We also looked at the effect of time. And as you can see for the two systems, as you increase time, the amount of format that was produced also increases. And of course, we also evaluated the load. clearly you can see that an increase in the load also results in an increase in the amount of format that is produced for the two systems, that is the functionalized and unfunctionalized MOF. So we then did some poisoning studies. Remember what we did was to insert the ruthenium complex inside the MOF. So how do we know that catalysis is taking place inside the pores of the MOF, or is it taking place outside the pores of the MOF? So we chose these thiols to do these poisoning studies reactions. And of course, you should expect bulky thiols not to move into the pores of the MOF because of steric hindrance. Probably their size much bigger than the pore size. So if they are not able to move into the MOF, it means they are not able to poison the catalyst. These thiols, they've been known to poison catalysts. By poisoning, it means they will reduce the catalytic activity. So as you can see here, we used these thiols, and this is the activity of your catalyst. This is a bulk thiol, as you can see. You can see that the yield that we obtained when you use this thiol is very high, simply because this compound is not able to move into the pores of the MOF, right? It remains outside. Therefore, it cannot poison our catalyst. So our catalyst remains very active. And of course, you can see that with these thiols, which are less bulky, you can see a drastic decrease in the catalytic activity of your MOF or your ruthenium sender. This is because these ones are able to penetrate the MOF channels, and of course, they will then poison our ruthenium sender. And as a result of that, the catalytic activity dropped significantly. So this is evidence that our catalysis was taking place inside the pores of our metal organic framework. And then we checked at the recyclability studies. We looked at both the pristine MOF as well as the ruthenium functionalized MOF. As you can see, the as-made MOF is very much stable over the 5 runs, whereas the ruthenium functionalized MOF showed some decrease or a gradual decrease in the catalytic activity. This could be due to, when you are using your MOF, the ruthenium may depart, or the ruthenium may form nanoparticles which disintegrate or which agglomerate, and then of course that also causes a decrease, a gradual decrease in catalytic activity. And then we also looked, but of course it's not very bad, because you can look from close to 98%, the activity drops to about 80% after 5 runs, which I still believe that this is it's a very good catalyst. And of course, the yields that we got were close to 98%, which shows the need for inserting the ruthenium complex inside the MOF. And of course, you can see with just the MOF only, you have an activity close to 60%. So that also justifies why we need to include these highly active complexes inside our MOFs. And of course, we checked with the pixel dependence. You can see with the MOF, the pristine MOF, JMS1 before catalysis and after catalysis, these peaks are dependence, then clearly match, which shows that the structural integrity of the MOF is preserved during catalysis. And of course, with the ruthenium function, so this is before the first cycle and after the 5th cycle, you can clearly see that you still have some peaks that are retained, and of course, which also confirms some degree of rigidity of our MOFs. It means that these catalysts are very good. But of course, you can see that they don't necessarily match, but of course, there are some similarities that are there between your catalyst before it's used for catalysis and after catalysis. Now, let's talk about the reaction mechanism. How are we forming formats from this reaction? If we have our MOF, so if you assume that this is your MOF backbone with your ruthenium 2 center, and of course where your ARA is represented by this your pisamine. The first step is elimination of your chloride from the ruthenium center. By so doing, it means you generate this open metal site, and of course then insertion of your hydrogen into the open metal site, you form that dihydrogen ruthenium complex, and of course the dihydrogen complex, the hydrogen also departs from that complex, and of course you then form with concomitant elimination of your HCl, you then form the ruthenium hydride, which we believe is our active material, and then there is insertion of carbon dioxide to form this ruthenium formate complex, and of course it dissociates to give formic acid. So this reaction is taking place under basic conditions of KOH. So that's what we proposed. There are other mechanisms in literature, but we thought this is a plausible mechanism for formation of your formate from carbon dioxide in the presence of KOH as a base. Remember, if you have an organic base, you form formic acid. But of course, if you have an inorganic base, you form the formate ion. Now, let's look at another different approach. And again, in this case, we looked at how best we can synthesize a metalloligand, and then we then apply that metalloligand in the synthesis of a MOF, which can be used for hydrogenation of carbon dioxide to formate. In this case, again, we use this dicarboxylic acid bipyridine MOF, and under appropriate conditions, we managed to introduce the palladium catalyst on the ligand, and of course we then used this metalloligand to synthesize a MOF, because already we have the palladium catalyst inside the MOF, and we took magnesium salt or manganese salt. We're able to isolate a metal organic framework in which your carboxylate moiety has 2 binding modes as illustrated in this scheme. So this is the structure of the MOF that we isolated. And as you can see, the metal center here is either, we used magnesium and manganese. So this could be magnesium or manganese. And you can see your palladium, which is coordinated to your chloride. And of course, at this metal center, you can clearly see that there is coordinated DMF, which is very important because it can be removed during activation to provide open metal sites, which enhance catalysis as well as adsorption of carbon dioxide. So this what you see here is the packing diagram of the MOF that I have just shown you. And as you can see, we have channels or spaces which runs along the C-axis. We say this is GMS2. This is some naming that we use in our research group to identify our MOFs. And again, so we wanted to apply this MOF for hydrogenation of CO2 to formate. But before you do that, you need to understand the stability of the MOF in different solvents. If, for example, in the previous slide on catalysis, Potassium hydroxide gave the highest turnover number of 4,896 under these conditions of 90 degrees Celsius and the pressure ratio of 1:3. This was very interesting. And again, the first base that was used also showed some activity, which is almost half that of potassium hydroxide. And of course, potassium carbonate, with potassium carbonate, you can clearly see that the turnover number was very, very low. And again, in the absence of a base, we don't see any formate being formed. So this also confirms that the base, and in this case, an inorganic base is very important in this reaction. And then in the absence of a catalyst, I think these are control experiments. In the absence of a catalyst, again, we are not getting any formate being produced. Okay, so we also varied the pressure, and as we vary pressure, you can see that in the presence of KOH as a base, the yield of the formate that is formed also increases. We also changed the temperature to 100, from 90 to 100, and again in a pressure ratio of 1:4, that is your carbon dioxide to hydrogen, and we obtained a turnover number of 9816 with a turnover frequency of 409. Interestingly, these two MOFs, your magnesium and your manganese MOF, are both containing the palladium complex, or palladium two sites in the MOF. The magnesium one shows a low activity. You can see under the same conditions, the magnesium shows a turnover number of 7,272 as compared to 9,816. This might be attributed to a number of factors. So you would all need to go into different programs to analyze the channels, the size of the channels. Of course, these materials are isostructural, these MOFs are isostructural, but of course, a closer look at their structural features shows that there are some minor differences in terms of the pore size, which could have played a role in the yield that is observed here. I said the magnesium is less active compared to the palladium MOF. And of course, we then looked at the activity of the linger. So this was more like a homogeneous reaction. So our linger with just your palladium coordinated to your ligands, that produced a turnover number of 4,080. This clearly shows that it is very important to heterogeneous homogeneous systems. So the incorporation of the palladium sites into the MOF is very important. As you can see that in a homogeneous reaction, you have a turnover number of 480, and in a heterogeneous system, the turnover number increases to 9816. Okay. And then we looked at the effects of temperature on the yield of formate that is produced in both cases. The green represents, the blue represents the magnesium-based MOF, and your orange represents the manganese-based MOF. As you can see, as we increase temperature for the manganese-based MOF, the optimum temperature is at 100 degrees. that is close to 9,800 something. And of course, the turnover number decreases due to decomposition of the format around 120. And for the magnesium-based MOF, the blue one, the blue bars, the turnover number increases from 90, from about 5,000 to close to above 7,000 at 100 degrees Celsius. And beyond 100 degrees, there is a significant decrease in the amount of format that is produced. We also looked at the effect of time and catalyst load on the turnover number of format produced. And again, an increase in time results in an increase in the amount of format that is isolated. As you can see, the turnover numbers here are increasing. The same also applies when you increase your catalyst load, the turnover number also increases. And then we look at recyclability studies. Let's start with the manganese-based MOF, which I say PD8MN JMS2A. So when you recycle your catalyst, you can see that there is a significant drop in the turnover number. And that of the magnesium, it also drops gradually, but not as significant as the manganese-based MOF. We looked at the PXLD patterns of these MOFs before and after catalysis. And we could clearly see that the structural integrity is maintained, but this information is not good enough to explain the observed significant drop in the catalytic activity of our MOFs, especially the PD at manganese JMS2A. Now, we turned our focus to look at other techniques which can assist us in interpreting these results. So what is happening inside the MOF that is causing the significant drop in the catalytic activity? We then did some term studies to look into this phenomena. The first A shows the term image. A shows the term image of your magnesium MOF before catalysis, and B shows the term image of your magnesium MOF after catalysis. You can clearly see that after catalysis, there is some agglomeration that is taking place. This agglomeration is due to formation of vanadium nanoparticles in situ during catalysis. And these nanoparticles tend to agglomerate, and as they agglomerate, the catalytic activity is reduced. So this explains why we saw a significant drop in the catalytic activity. C shows the term image of your manganese MOF before catalysis and after catalysis. And as you can see, the formation of nanoparticles here is much more significant when you compare it to this image B for the magnesium MOF. So this may also explain the observed significant drop in the catalytic activity of the manganese MOF that we saw, because you can clearly see that there are some nanoparticles that have agglomerated. We also carried some XPS studies. Of course, I did not include those results here, which also confirmed that there were some nanoparticles in the used catalyst. So, you know the reason why we anchor catalysts on the walls of the MOF is that we want to prevent agglomeration. But of course, during catalysis, agglomeration may take, nanoparticles may be generated in situ. So I think it's very important to look at all these considerations. What kind of solvents can we use which may also prevent a formation of nanoparticles? Because when you are working with a base such as potassium hydroxide, you also need to consider things like the concentration, because high concentration can also lead to formation of nanoparticles in your MOF, which may then reduce the catalytic activity of your MOF. So, ladies and gentlemen, this is the research that we have been doing in the past 3 or 4 years. And of course, we are still working on different systems for hydrogenation of carbon dioxide to fine chemicals, such as you have just seen now, we have we produce deformate. We are also targeting methanol, but with methanol, we are looking at natural systems. We are looking at how we can work with the biological systems which are integrated with the metal-organic frameworks to produce methanol. So that research is ongoing at the present moment. So this brings to the end of my presentation. I want to thank the Royal Society for funding this project and the African Academy of Sciences. I also want to thank IUPAC, FOS Agro, and the United Nations Education, Scientific and Cultural Organization for the Green Chemistry Grant, which also allowed me to do some of this work that I presented today. So from this work, we've managed to get some outputs. We've managed to get, I think, about 3 publications from hydrogenation of CO2 using metal-organic frameworks. And of course, we had 2 students graduating last year. Unfortunately, I did not get Nyasha's picture in her regalia, but these are some of the outputs that we were getting from our research. Thank you very much, ladies and gentlemen, for listening to my presentation. I hope you learn 1 or 2 things during this presentation. So I will leave this time to the chair of this session.
Oh, thank you very much, Dr. Mehlana, for the nice presentation and nice research. Yeah, a lot of result here. And now I offer to the audience who has question. Please raise your hand, or you can write in the chat box. Okay, one raise hand. Yes, Mr. Yesi Permana, Dr. Yesi Permana from ITB. Yeah, please the question. Yeah.
Thank you, Dr. Witt. Thank you a lot. Thanks a lot to Dr. Mehlana for the presentation. Few questions about the catalytic activities of the ruthenium or palladium anchoring GMS. Will it be possible for us to think that it is actually not the ruthenium to give the double activity product in comparison between homogeneous ruthenium complexes that you did or palladium complexes that you did as a benchmark and the ruthenium or palladium anchoring to the GMS MOF?
Okay, thank you very much for the question. I'm not so sure I understood your question very well. So you are saying, is it possible to think that it's not ruthenium that is active? Is that so?
Right. So if we look at your reactions, there are possibility as well that the solvent, as you use the ethanol and ethanol giving the hydrogen source to the carbon dioxide after initiation with the base, then we think that actually ethanol or other alcohol solvents is the hydrogen source apart from the hydrogen, pressurized hydrogen as the hydrogen source. In that way, ruthenium 2 or palladium 2 probably act not only as the hydrogenation catalyst, but also the metal in the MOF acting as the Lewis acid to initiate the proton transfer.
Oh, okay.
What is your
I think I
comment
got
on
your
this?
question. Thank you. That's a very intelligent question, I must say. But of course, yes, what you have proposed is very much possible. But from the studies that we did, we looked at the ruthenium psi-amine complex on its own. It's a dimer. So this was under homogeneous conditions just to check, and we realized that it was active, giving a yield of about 24%. But once this is then grafted into the MOF, we saw a significant increase in the amount of format that was formed. And then we attribute that to the ruthenium-2 that was grafted to the MOF. In terms of the solvent that we used, ethanol, most literature reports shows that in the absence of solvents such as ethanol, which are very important in facilitating the proton transfer, at times you don't get any product in that case. But of course, I would suggest that control experiments would be very, very useful to actually ascertain that what we have proposed is not contributing to the formation of format from our catalytic system. Thank you.
Right. Thank you. So I think there is also a place for thinking a synergetic effect between ruthenium or palladium active sites and also the metal in the MOF itself. For instance, the manganese 2, it is also probably active in acting as the facilitating proton transfer, I mean. If you don't mind, I have another questions about the recycling of the ruthenium GMS for up to 5 times, that we could see either ruthenium or palladium. We could see a drop of activity. Did you see any leach of the ruthenium or palladium by ICP or XRF, and comparing the number of the metals between palladium with manganese, for instance?
So the recyclability studies, we did some ICP studies, and then we realized that the amount of manganese or ruthenium that is detected is very, very low. It's negligible. So in that case, we then said the catalytic results is mainly due to heterogeneous catalysis. But of course, the values that we got for these metals in solution was very, very negligible. So we did those kind of studies. And then in terms of the manganese or magnesium being active, we could not get a model, a proper model to use. But what we then did was to take the metal salts that we used during synthesis of MOFs to try and see if they have an effect towards the formation of the format. And under the conditions that we used, we did not observe any format being produced. But of course, like you rightfully pointed out, that manganese, we know there are some reactions that are also catalyzed by manganese in literature with a very, very good yields. But of course, in our case, when we used the metal salts that were applied in the synthesis of MOFs, under homogeneous conditions, we did not observe any format being formed.
Thank you, Dr. Mehlana.
Okay, thank you very much for the questions.
Okay, thank you, Mr. A.C. Permana, for the question. And here is a question in the chat box from Miss Nicole Zimbabwean, chemist student. I think she is from Zimbabwe, but currently she is studying in the US, I think, yeah. Yes. The question are there any industries in the Zimbabwe or South Africa that you have worked or with currently or plan to work with recycle their carbon emission?
Okay, the question is, are there industries in Zimbabwe or South Africa that I'm working with or that I intend to
Yes.
apply my MOFs? Okay, thank you very much for that question. So basically, if you look at Zimbabwe and South Africa, these are developing nations, and there's a lot of carbon dioxide emission in terms of power plants that are producing carbon dioxide, as well as cement manufacturing companies. At the moment, I can't say that I've approached the companies to look at these technologies because there's still a lot of work to do, as you have seen. But of course, if there is something that comes out in terms of which is very promising, if we get materials which are very promising in terms of the turnover number and the stability, then definitely we can sell these ideas to these companies. Already, there are some companies in Zimbabwe, like the cement manufacturing companies, which also want to target the net zero emission by 2050. So these are some of the technologies which they may want to adopt in the future, because obviously that process where you manufacture your cement, you also have your CO2 that is coming out. So at the present moment, no. I don't have any companies that I've worked with, but of course, if we get very promising materials, certainly there are companies that we can approach and then sell these ideas, because everyone knows about these net zero emissions by 2050, and companies really want to do something to contribute to that cause. Thank you.
Thank you for the answer. Yeah. Wait.
Please, can I ask question? Dr.
Hi, please, yes. Yes, please, Dr. Yuni Krishnandi from Universitas of Indonesia.
Hello. Yeah, sorry, I'm a bit late, but this very fascinating lecture. I'm interested in this reproducibility of the catalyst. Yeah, it seems that the catalyst can stand the condition several times. Regarding that, I just wonder whether is there any like suggestion or tips to maintain this reproducibility, because as we know that can be very fragile. This the organic the organic linker. Sometimes they cannot stand the harsh condition. Yeah, and also high temperature. Yeah, thank you.
Oh, okay. I think you were breaking a bit. I'm not so sure if I got your question correctly. So you were talking about the stability of the MOF. So you were saying, can we improve the MOF?
Yeah, how to improve that? The reproducibility.
Oh, okay, thank you. So now there are several strategies if you want to design metal organic frameworks for heterogeneous catalysis, and if you also want to maintain the structural integrity of your MOF during catalysis. One way would be to choose, as you can see in my presentation, when I started with the first MOF, it's a lanthanide MOF, right? Because they have high coordination, they can accommodate a high coordination geometry, they tend to be very stable during catalysis. That is one way to do it. If you use transmetals, which can have a coordination number of up to 6, at times these are not very stable. But from literature, if you work with lanthanides, especially zirconium, it has been also reported to be very, very stable in catalysis reactions. And the other consideration that you also need to look at is your synthetic conditions. Try to make your MOFs using solvothermal techniques at around 120 degrees. Why? Because during catalysis, this is the temperature that you are playing at. And normally, MOFs or crystals, they tend to form at that temperature at 120. So it means that also brings some form of stability. Recently in literature, there are other techniques that are being applied to stabilize MOFs. You have rightfully said that MOFs tend to collapse upon removing solvent molecules or during catalysis. So other researchers have looked at the possibility of using polymers to support the organic linkers in the metal salts in your MOF. And that has an effect of increasing the stability and also increasing the surface area of your MOF. Because remember, the moment you remove your guest molecules or the solvent molecules that are in the MOF, that are trapped during formation of the MOF, your MOF may collapse, or there may be some structural distortion, which may significantly reduce the surface area. But if you are using polymers, there are certain polymers which can support your organic linker and your metal source or your metal ion so that they don't collapse. If you look into literature, that a lot of scientists are looking into that and how they can possibly exploit that to stabilize the MOF, regardless of the nature of the linker that you have used in the metal source. So definitely there are certain approaches, like of course using lanthanide metals, preparing your MOFs at very high temperatures, and of course using polymers to stabilize your MOFs. Thank you.
Thank you so much for the tips here.
Okay, thank you. Yes, I see a hand up. Can you go ahead?
Okay. Can you hear my voice?
Yes, I can hear you.
Okay, thank you, Dr. Mehlana, for nice results and interesting presentation. I want to ask about the regarding the process of CO2 reduction to formate. The greatest challenge in reducing the carbon dioxide is that the carbon dioxide molecules are highly stable. You know, the linear molecules, if you want to reduce using the heterogeneous catalysis, for example, you need to activate the carbon dioxide molecules. You need to bend that linear stable molecule so that it can undergo hydrogenation or reduction reactions. So in your experience, is there any rational design, or I can say rule of thumb, in how we prepare our catalyst? For example, in this case, MOF, of course. I mean, how do you choose the metal of the metal clusters? How do you select the ligand or the organic linkers? And is there any way we can rationalize the design of our catalyst for specifically for the CO2 reduction? Thank you.
Okay, that's a very important question, I must say. But of course, we have a number of approaches that you can use with regards to carbon dioxide hydrogenation to form it. You need to consider the adsorption capacities of the MOF that you want to prepare. Because the first thing that happens before catalysis takes place is adsorption of your carbon dioxide, right? So the nature of the metal that you choose must allow for adsorption of carbon dioxide. For example, I would tell you that I use the lanthanum because lanthanum, the lanthanum MOF allows for a high coordination number. And you would then see that when the MOF is formed, there are some solvent molecules that are coordinated to the lanthanum metal ion, right? During activation process, so this is the process where you want to remove all the solvent molecules, your DMF, your water, etc. The DMF, which is coordinated, is removed. And as you remove that DMF, during adsorption studies, it has been shown that because you have open metal sites, it increases the amount of carbon dioxide that is absorbed into your MOF. So that is, from a practical point of view, you should consider that. Okay, and then you said that the carbon it's thermodynamically stable. The question is, how do we activate it? Right? How do we activate carbon dioxide? It's very stable. So
because
those are some of the things that you need to think
energy
about.
barrier will be so high.
This is why you see that we used a wide range of bases. We used a wide range of bases. We had potassium hydroxide, sodium hydrogen carbonate, and some organic bases. And depending on the strength of the base, at times you should be able to form your format. If you use a weak base, at times you may not be able to achieve that reaction. So the base is very important. The next thing, your carbon dioxide, before the reaction, in a heterogeneous system, it has to dissolve. So the solvent that you use during catalysis must allow for carbon dioxide to dissolve. If that solvent does not allow for carbon dioxide to dissolve, then it will be very difficult for that particular reaction to take place. For example, I will tell you that in literature, I've come across a situation where a DMF has been used as a solvent for hydrogenation of carbon dioxide to form it. This is not my work. And because carbon dioxide tends to dissolve so well in DMF, they got a very high turnover number. So these are some, if you want to move, for example, because if you want to move from metals to metal-free catalysis, for example, we have what we call, in my last lecture, I talked about what we call frustrated Lewis pairs, which are basically compounds with both acidic and basic sites. These ones, they are able to split hydrogen. They're also able to activate hydrogen, right? So what is important is that the activation of hydrogen, it will take place at the acidic site, right? And so in a Lewis, in a frustrated Lewis pair, and if it is grafted into a MOF, it must be in such a way that the carbon dioxide must not bind strongly to the frustrated Lewis pair. In other words, if it binds strongly, it poisons the catalyst, right? It means you won't be able to remove it from that site. So it's very important. And of course, if it's binding strongly, you will then also need to consider reaction. Which one are you going to add first? Are you going to add hydrogen first so that it's split? Or are you going to add carbon dioxide first? So all these are practical considerations that you can think about. But from a heterogeneous point of view and from a MOF chemistry point of view, the solvent that you use is very important. Your carbon dioxide must dissolve. The base that you use, okay, it's also very important. As well as the metal ion that you use during MOF synthesis, it must allow for adsorption of carbon dioxide. It must have open metal sites once it's in the MOF. The linger, you also talked about the linger. The linger, has also an effect depending on whether the linger is functionalized. I can tell you that, for example, if you have an NH2 group on your linger, that will also tend to increase the amount of carbon dioxide that is adsorbed into your MOF. Okay. So all these things can be considered in terms of designing your catalyst for heterogeneous catalysis. Thank you.
Okay, thank you, Dr. Mehlana. Bu Witri, can I still ask one question?
Yes, please.
Okay, thank you, Dr. Mehlana. You mentioned a lot of or several points to be considered, and I also came to my knowledge that in the activation of carbon dioxide or in the absorption of carbon dioxide, you know, the particle size or the crystal facets of MOF or other heterogeneous catalysts are also important. Can you also comment on this? I mean, for example, in the metallic catalysis, we will prefer the 1,1,0 crystal facet or 1,1,1 crystal facet. Is there any phenomenon or any similar phenomenon we can observe in MOF catalysis?
Oh, okay. Thank you very much. So I think that's you raised a very, very interesting point in terms of the crystal size and, of course, the orientation of these crystals during catalysis, which I want to believe that it has an effect on the yield of the product that is formed. But from my own experience, from what we have done so far, we haven't really looked at the effect or the facet size of these crystals in terms of the yield that we are likely to get and even its effect on adsorption of carbon dioxide and hydrogen into the MOF system. But I think it's something that is very interesting to look into in future and see what that can give us. But our work, we haven't really gone to that point. But of course, what you tend to realize with particle size in catalysis in general is that particle size is very important because for large particle sizes, you then see that normally you don't get a high yields because, of course, diffusion may be restricted into those sites or the surface area of your MOF. Where you are doing catalysis will be also reduced. So if you have very small surface, if you have a very small particle size, you should be able to get a high yield. But in terms of the orientation and all those things, we haven't really looked at those aspects. And I must acknowledge that that is something that is very interesting to look at in future. Thank you.
Thank you, Dr. Mehlana. So we can see that the possibilities, I can say, limitless in heterogeneous catalysis, especially in MOF catalysis. Thank you.
Oh, okay, thank you very much.
Okay, thank you, Dr. Greenprick, for the question. Are there any questions from the audience? If not, I will ask a question to Dr. Mehlana. In the building of MOF, in the first you synthesize the ligand and then connect with the palladium metal in the center of the metal, I think. And after that, you build the MOF. As I understood, it's called as a building block approach here. I have a question. How did you get the MOF? It was by sulfothermal method or by diffusion method? Because to keep the palladium to be inside and not destroyed by the heating or by the treatment during the synthesis is quite difficult, I think. And I have issue also in my lab that we try to build like cisplatin complexes, and then after that we try to build a MOF, but still not successful in this case. Maybe you have suggestion about this step.
Oh, okay. I'm not so sure if I got your question correctly. So you said, how did we manage to isolate the MOFs with the complexes inside? Is that the question?
Yes, right.
Oh, okay. It depends. So remember what I said earlier on. Okay. I wanted to share my presentation. Can you see that button? Okay, so in my talk, when I started the presentation, I showed you some diimine complexes, and I said we also introduced the metals such as your ruthenium, iridium, and rhodium, and we then tried to make some MOFs using those diimine complexes. We were not successful in most cases because of hydrolysis. this is the reason why we then shifted to using rigid linkers to try and synthesize these MOFs. At times, it's about the reaction conditions that you use. Certain reaction conditions may not allow, may not favor formation of MOFs. And of course, with the crystal engineering knowledge background, you may say that because I have a carboxylic acid functionality, I have a nitrogen side, I have a metal salt, I should be able to form a MOF. It may not always be the case because maybe your organic compound or your organic complex is disintegrating under those conditions such that you may not be able to isolate them off. If it's not disintegrating, then you need to play with the reaction conditions. I showed you some complexes that were made by Spelele Malaza. She could not isolate MOFs under solvothermal conditions, but she was able to isolate them under solvent evaporation. But of course, that took quite a very long time, from 30 to 60 days. And of course, I also said that once you form MOFs at room temperature, they may not be very useful, especially for heterogeneous catalysis. But MOFs that you form under solvothermal conditions at about 120 degrees, they tend to be very stable during catalysis. Because normally our catalysis, we do it around from 80 up to 120 degrees. So if your MOF is forming around 120, you shouldn't have a problem, right? But I think try to look at are your complexes not disintegrating in the solvents that you are using? Okay, if you not play with the reaction conditions, change the solvent systems. You can try a combination of solvents. I'm just telling you from my experience. You can try a combination of DMF, DMAC. You can try a combination of DMF, ethanol, etc. And of course, you can vary all those reaction temperatures, and of course, the concentration of your starting materials. At times, you target crystals because you want to elucidate the structure, but at times you may get a powder. That powder, it does not necessarily mean that it's not a MOF. It only means that you will need an advanced technique to solve the structure using powder data. But if you are targeting crystals, you need to play with the reaction conditions that will allow formation of crystals. In working with the dilute solutions, right? It also ensures that you may be able to isolate the MOFs. So I think that's what I would say for now, is that try to play with the reaction conditions. You may want to just check probably if you are not getting any crystals, or if you are just getting a solution, try to just check whether your organic compounds or your complexes have not yet decomposed, because that is also a possibility. And if they do, you may not get what you want. It may, if it crystallizes out, it crystallizes out as something else that is different to what you would expect. Thank you.
Yes, okay. It's mean that we should try several variation for the synthesis.
Yes. I think I can show you this. Let me see if I can go back to this. Okay, I'll try to use this one. Okay, so just as an example to what we have said. Okay, so when we started, we were using these diimine ligands to make these complexes. So these diimine were made by Nyasha, and what we then realized that when we wanted to use these, as you can already see, we already have our carboxylic acid groups here, which can react with a metal salt to form a MOF. And of course, we are already happy because we already have our catalyst inside. But we realized that because this is a diimine, it hydrolyzes, and we're not able to form MOFs. So that was the challenge that we faced at the beginning of our research. But of course, these were highly active when we carry out hydrogenation studies, as you can see from these results. This is the reason then we then moved to these complexes, which were made by Spemalaza, and then we're able to isolate the MOFs. But of course, the biggest challenge here is that the reaction time was very long because this was carried at room temperature. As you can see, we have 30 days to isolate the crystals. And for this one here, we have 60 days to isolate. So you need to look at how best you can optimize the reaction conditions so that you may then isolate them. But if you want to work on heterogeneous catalysis, I would advise you to work with the thermal conditions. But of course, isolating this is a plus because it shows that it is possible to make these MOFs using these pinza ligands.
Yes, yes. For the single crystal, maybe we can try diffusion, but for upscaling, we can try with the sulfothermal, but with appropriate condition.
Yes, yes, yeah. For upscaling processes, we can try with sulfothermal. I mean, maybe we can also try mechanochemical and see whether we can get the same structure.
Yes. Thank you very much for the answer and explanation. Are there any questions?
Bu Witri, may I ask just short questions? One more.
Please, Pak Yesi.
Yeah, Dr. Mehlana, since we have this complexes with carboxylic acid as the coordinating site to the metal MOFs, then do you think adding some protons will not activate the reaction, since addition of protons instead of base will create kind of a weakening coordination of the ligand to metals? Then we have a better vacant sites number. So the open sites of the metals will increase because of the weakened coordination of the carboxylate on the metals of the MOF. Then one of the linkers will be kind of weakened or dissociate to create an open sites, which is probably one of the reasons to increase. Is there any experiments on this?
Not yet. We haven't done those kind of experiments. But what you propose, I understand that, and I think it must be possible. But in our case, like I said, the solvents that we normally use for synthesis, these are the ones that coordinate to the copper, and we can increase the open metal sites by activation. So that's what we
by increasing the temperatures.
We haven't done anything similar to what you have suggested.
Okay. Yes. So what I'm saying is, instead of increasing temperature to activate the MOF, probably we can run the reactions at mild temperatures by just modulating the coordination strength of the linker to the metals by adding some small proton amount.
Oh, okay. Yeah, that should
just
be
an idea.
I think that's interesting, and I think it's something that can be explored and see if we can achieve the same results with the activation. But of course, the advantage of your method is that we can retain a high surface area, because the times when you activate at high temperature, you also tend to distort the MOF, which may then reduce the surface area. But with mild activation and your suggested method, it means we can also increase the surface area of the MOF, which is very important, especially for catalysis.
Right.
Yes.
Okay, thank you so much.
Oh, okay, thank you.
Okay, and I think the time is now over here. And many thanks again to Dr. Kif Mehlana for the nice presentation, and for all audience. I would like to thanks also for the for joining this meeting. Yeah, and hopefully we can meet again around 28th of May. I will have one guest lecture from Gauss about scientific lecture, but from Gauss.
Oh, okay. Yes.
And here I will present the certificate. I will present it to Dr. Kif Mehlana from our institution. Yeah, we would like to thanks for giving the nice guest lecture to our faculty for Kif Mehlana.
Okay, thank you very much for the certificate, and
hopefully the near future we get to another. Okay. And we can like start a new collaboration for like a project about MOF. It's Indonesian, between Indonesia and Zimbabwe maybe.
Okay. Thank you very much. I am very much open to collaborations in this area of my research, and certainly we can do some amazing chemistry together. Already there were very interesting suggestions from the questions, very intelligent questions we asked today, which also stimulates the way we are going to think and moving forward. I also want to take this opportunity to thank everyone who attended this presentation from my first lecture and to my second lecture. Special thanks also go to my students and my colleagues. I see Faith is here, and Spelele, one of the students who was also working on this project, is among us, which I want to believe that that support is very good. So thank you very much for inviting me to share my knowledge on the sensing and catalysis. I hope this is the beginning of many lectures to come. Thank you.
Yes. And for closing statement, yeah, maybe we can take picture together and open the video. Yeah, please the audience open the video.
Yeah, yes, the picture before we can go, yes.
Okay. Yes, One, two.
Where is the 1, 2, 3?
Some of my colleagues are coming from different university, from ITB and then from IPS. Yeah, I'll take the screenshot first. Betul, ya, start ya. Screen number 2 ya, I'll check. Yeah, there is iPhone 20 here. Yes, appear here.
Oh, it has started. I did not hear the 1, 2, 3.
Okay.
Okay.
I'm sorry, I have bad connection here. Screen number, only 2 here. Maybe some of our students are leaving because they have another lecture.
Oh,
okay. Thanks again for the audience for coming to this meeting, and I would like to acknowledge to Dr. Mehlana for giving the nice lecture, and hopefully we will meet again for the next occasion. I will close the session. Wassalamualaikum warahmatullahi wabarakatuh.